Welcome to this deep dive into the world of variational autoencoders.
Wow.
We're calling them VAEs for short because, well, nobody's got time to say variational autoencoders every time, right? So imagine trying to capture the essence of, say, every cat picture on the internet. That's the kind of power we're talking about here. VAEs are generative models, which means they can actually learn the underlying patterns in complex data. Think images, text, music, and then use that knowledge to generate brand new realistic examples. Pretty cool. Huh?
It is quite impressive. They combine deep neural networks with a statistical technique called variational inference.
Okay, you've officially used the word inference, so you know I'm going to need you to break that down for us. What's the big deal with generative models? What can they do that other machine learning models can't?
Think about it like this. You've got your regular weather app, right? It tells you if it's going to rain tomorrow based on today's conditions. That's like your standard machine learning model. But a generative model, it's like having a full-blown meteorologist in your pocket. They're not just predicting the weather, they're simulating the whole complex system, how temperature, pressure, humidity, everything interacts to create those weather patterns.
So it's not just about predicting an outcome. It's about understanding the whole process. That generated the data in the first place.
Exactly. And that opens up a ton of possibilities. Let's say you're a scientist trying to design a new drug. A generative model can help you understand how different molecules are structured, and then generate new ones with specific properties. Or imagine you're trying to spot anomalies, like fraudulent transactions in a bank. A generative model can learn the normal patterns and then flag anything that looks fishy.
Okay, now I'm seeing why this is such a big deal. We're actually going to be looking at two key sources today to get a handle on VAEs. Some excerpts from a research paper on denoising autoencoders, and excerpts from the book, An Introduction to Variational Autoencoders by Kingma and Welling. Kind of the VAE Bible, right?
Absolutely. That's a seminal work in the field.
Perfect. So our mission today is to equip you, dear listener, with a solid understanding of VAEs, their inner workings, their strengths, and the challenges they address. By the end of this deep dive, you'll not only be able to impress your friends at parties with your VAE knowledge, but you'll also have a glimpse into the exciting possibilities they unlock.
And we might even uncover some surprising connections to other machine learning techniques you might already be familiar with.
Ooh, love surprises. Okay, so let's start with that research paper on denoising autoencoders. It focuses on a precursor to VAEs, and it highlights a pretty key challenge when it comes to modeling complex data like images.
Right. The idea behind a denoising autoencoder is pretty clever. You take an image, add some noise to it, and then train the model to reconstruct the original clean image. The problem is, as the paper points out, these models tend to rely on some pretty simplified assumptions about the relationship between the original and noisy data.
So it's like trying to reconstruct a masterpiece painting after someone splattered paint on it randomly. You might be able to get the general shapes, but you're going to miss a lot of the details.
Exactly. And when you're dealing with something as complex as a high-resolution image, those details matter. That's where VAEs come in. They offer a more powerful and flexible approach to modeling these complex relationships.
Okay, I'm intrigued. Give me the VAE elevator pitch. What's the big idea?
The big idea is to learn a mapping between the complex world of the data, like those images we're talking about, and a simpler hidden space called the latent space.
Latent space. Sounds like where all the cool kids hang out.
Well, it's where all the essential features of the data hang out. Think of it like a map. You've got this complex geographical area, but the map simplifies it, showing the key landmarks and relationships. That's what the VAE is doing. It's taking all that complex data and compressing it into this simpler, more manageable, latent space.
So in the case of images, instead of trying to model every single pixel, the VAE is saying, hold on, let's figure out what the key features are, the shapes, the textures, the overall essence of what makes this image, this image.
Precisely. And this mapping between the data and the latent space is done by two key components of the VAE, the encoder and the decoder.
Right. Dynamic duo time. Let's start with the encoder. What's it encoding?
The encoder takes the input data, let's say that cat picture, and maps it to a distribution in the latent space. And here's where it gets really interesting. The encoder is probabilistic.
Probabilistic. So it's not just saying, here's the exact location of this cat on the map.
No, it's more like saying, okay, the cat is probably somewhere in this region. It outputs a distribution, usually a Gaussian distribution, which captures the uncertainty associated with that mapping.
So instead of a single point on the map, it's like a blurry circle, right? Because even if two cats look very similar, there might be subtle variations that the encoder wants to capture.
Exactly. And this probabilistic nature is crucial for the VAE's ability to generate new data later on. If it were deterministic and only output a single point, we'd end up with the same cat picture over and over again.
Now, that would be a boring internet. But wait, the paper also mentions this thing called amortized inference. What's that all about?
Think about it this way. You've got this map, and you need someone to read it for you. Amortized inference is like having one super efficient map reader who can instantly understand any map you throw at them. Instead of needing a specialist for each region, it means that we can learn a single encoder network that can handle all of our data points. This makes VAEs incredibly efficient, especially when you're dealing with huge data sets.
So thanks to this trick, VAEs can handle those massive image data sets that are all the rage these days without breaking a sweat. That's why they're a go-to for things like image analysis. You've got millions of pictures to work with.
That's a great way to put it. Efficiency is one of the key reasons. VAEs are so popular in practice.
Okay, so the encoder compresses the data into this latent space, like a super efficient map reader.
Okay.
But what about the decoder? What's its role in all of this?
The decoder is the artist of the VAE. It takes a point from that latent space, a point on our map, and uses it to generate a sample in the original data space. So if the encoder took that cat picture and mapped it to a point representing catness, the decoder can then use that point to generate a whole new cat picture.
Wait, so you're telling me that by tweaking a single number in this latent space, I could make a cat's ears pointier?
Yeah.
Or its fur fluffier? That's wild.
That's the power of generative models.
Sure.
And just like the encoder, the decoder is also probabilistic. So even if you feed it the same point in the latent space multiple times, it will generate slightly different output.
That makes sense. Otherwise, we just end up with clones of the same cat. And we know that in the real world, no two cats are exactly alike. So we've got our encoder, which compresses the data into this latent space, and our decoder, which reconstructs it back into something we can see. But how do we actually train this whole system? How do we make sure the VAE is learning the right things?
That's where the training process gets really interesting. But before we dive into that, there's one more piece of the VAE puzzle I think you'll find fascinating, the reparameterization trick.
Ooh, a trick. I love tricks. The paper makes it sound like this is some kind of magic ingredient.
It is pretty magical. It's a clever technique that's absolutely essential for training VAEs efficiently. Remember how we said the encoder is probabilistic, outputting a distribution rather than a single point?
Yeah, that was the whole blurry circle on the map thing, right?
Right. Well, that randomness introduces a bit of a headache when it comes to actually training the model, to train neural networks. We use an algorithm called backpropagation, which relies on being able to calculate gradients, these little nudges that tell the network how to adjust its parameters to get better at its task. But randomness can mess that up. You can't easily calculate a gradient through a random sampling process.
It's like trying to figure out the exact path a pinball took when it's bouncing all over the machine.
That's a great analogy, and that's where the reparameterization trick comes in. It's a bit like rearranging the pinball machine so that some of the randomness happens outside the main game. We separate out the random part of the process from the deterministic part, allowing backpropagation to work its magic.
Honestly, when I first read about this, my head was spinning. It felt like some kind of mathematical wizardry. But then I thought about it like rearranging a messy toolbox so that all the tools have their own designated spots. It's still complex, but at least there's a system to it.
That's a fantastic way to think about it. And it's precisely this reparameterization trick that makes it possible to train VAEs effectively using gradient-based methods.
Okay, so we've covered a lot of ground already. We've talked about the big picture of generative models, the limitations of those denoising autoencoders, and the core idea behind VAEs with their encoder-decoder and this magical reparameterization trick. But there's still so much more to explore.
Absolutely. We've only just scratched the surface.
Well, in that case, let's take a quick breather. And then we'll dive even deeper into the VAE world. We'll be back in a flash to unravel the mysteries of training, explore the potential of those multi-layered latent spaces, and maybe even venture into the realm of normalizing flows. Don't go anywhere. Welcome back, everyone. Before the break, we were talking about how training a VAE is like this balancing act between two objectives, reconstruction and regularization. And I think I'm starting to get the gist of it, but something that really struck me in the Kingma and Welling book was this idea that a VAE is basically like an autoencoder. with the special regularization term. Can we unpack that a little bit? I think it might help solidify things for me, and I'm sure our listeners are curious too.
Absolutely. It's a helpful way to understand how VAEs differ from standard autoencoders. Both aim to learn a compressed representation of the data, but their approach differs slightly.
Okay, so just to recap, a regular autoencoder has two parts: an encoder that squishes the data down and a decoder that tries to puff it back up right.
Precisely. And the autoencoder's main goal is to minimize the difference between the original input and the decoder's output. Basically, it's trying to preserve as much information as possible, even when it's squeezing it through a bottleneck.
But how does the autoencoder know what information is important to keep? Couldn't it just end up garbling everything?
That's a great question, and it highlights a key challenge with standard autoencoders. Without any constraints, they could just learn to memorize the training data without really understanding the underlying structure. Imagine trying to compress a giant library into a single book. You might be able to cram all the words in there, but you lose all the meaning and organization.
So it's like a parrot that can repeat words, but doesn't actually understand the language. That's not very helpful if we want to generate new data or really grasp how the data is created.
Exactly, and that's where the special regularization term comes into play. In VAEs, it acts like a librarian, guiding the VAE to organize information in a meaningful way.
So it's adding a penalty to the VAE's objective function. If the latent space gets too messy and disorganized.
You got it. And remember how we talked about the VAE? Encouraging the distribution in the latent space to resemble that standard Gaussian distribution, that nice bell curve.
Yeah, that was the regularization objective.
Well, that's exactly where it comes in. The regularization term in a VAE's objective function is basically measuring how different the distribution learned by the encoder is. From that simple, well-behaved Gaussian, it's like a scorecard that tells us how well our VAE is balancing between accurately reconstructing the data and keeping things tidy in the latent space.
So it's like the VAE is trying to walk a tightrope. On one side, it wants to minimize the reconstruction error, just like standard autoencoder. On the other side, it wants to keep the latent space representation close to that nice Gaussian distribution. And the regularization term is the balancing pole that helps it stay upright.
That's a fantastic analogy. It's all about finding that sweet spot between minimizing reconstruction error and keeping the latent space structured and regularized.
This makes me think of those beautiful visualizations of latent spaces I've seen, where you can see how different data points cluster together based on their features. It's like taking a complex data set and turning it into a map where you can see all the continents, countries, and cities laid out in a way that makes sense.
Yes. Those visualizations really highlight the power of VAEs. By learning a structured latent space, they allow us to see and explore the relationships between data points in a way that wouldn't be possible with a standard autoencoder. It's like having a map that's not only accurate, but also easy to read and understand.
But isn't that assumption of a Gaussian distribution a bit limiting? What if the data is more complex than that?
That's an excellent point, and it leads us to some of the more advanced techniques that researchers are developing to make VAEs even more powerful. But before we get to those, I think it's worth digging a bit deeper into how this regularization term actually works in practice. We've been throwing around the term Gaussian distribution a lot, but what does this regularization term look like mathematically?
Okay, now you're talking my language. Just kidding. I'm more of a visual learner. But I do remember this thing called KL divergence from our deep dive on information theory. Didn't it have something to do with measuring how different two probability distributions are?
You've got a great memory. The callback-Leibler divergence, or KL divergence for short, plays a key role in VAE regularization. It's used to calculate the difference between the distribution learned by the encoder and that chosen prior distribution, which in most cases is our friend, the standard Gaussian.
So the smaller the KL divergence, the closer the encoder's distribution is to that nice, well-behaved Gaussian right. And that's what the VAE is aiming for during training.
Exactly. And the KL divergence is baked right into that balancing act we were talking about earlier. It's all about finding the right balance between minimizing reconstruction error and keeping that latent space representation in check.
Okay, I'm starting to see how this whole latent space thing is more than just a mathematical trick. It's like a secret code book for understanding the data. And the KL divergence is the key to deciphering it.
What's fascinating here is that this regularization term, by encouraging a structured latent space, actually helps the VAE become better at generation too.
Now that's what I call a win-win. But I'm curious, how does having a more organized latent space lead to better generation?
Well, imagine trying to navigate a city without a map. You might eventually find your way around, but it would be a lot of trial and error. Now imagine having a map where similar places are grouped together, all the restaurants in one area, all the museums in another. It would make exploring the city much easier and more efficient.
So if I wanted to generate a picture of a cat with a specific fur pattern, I could take a point in the latent space, that represents a cat, and move it slightly in the direction that corresponds to, say, tabby stripes or calico patches. And because the latent space is structured, I wouldn't have to worry about accidentally changing the cat's ear shape or eye color.
Exactly. By imposing structure on the latent space, we're essentially creating a map where we can navigate and explore different variations in a controlled way.
And that wouldn't be possible with a standard autoencoder. That's just focused on cramming as much information as possible into the latent space. It might learn a representation. That's great for compression, but not very useful for generating new and interesting cats.
Precisely. The regularization term in VAEs is what unlocks this potential. For controlled generation and exploration, it's what makes them truly generative models, not just fancy compression algorithms.
I feel like we've really peeled back the layers on VAEs today, but there's still so much more to uncover. We've got those advanced techniques like normalizing flows and hierarchical VAEs waiting in the wings, and I, for one, am ready to dive in. But let's give our listeners a chance to catch their breath. Before we embark on the next leg of our journey, we'll be back in a jiffy to explore the cutting edge of VAE research. And we're back, ready to jump back into the VAE world. I'm feeling like a seasoned explorer now, map and compass in hand, prepared to navigate the wilds of the latent space.
Excellent. And I have just the terrain for our next expedition. Multi-layered latent spaces.
Ooh, multi-layered. So instead of having just one of those map-like latent spaces, we could have a whole stack of them, like those Russian nesting dolls, but for data.
Exactly. Imagine a map of a city. You could have one layer showing the overall layout, the neighborhoods, the parks, the major roads. Then you could zoom into another layer, showing individual streets and buildings. And you could even go deeper, showing the rooms inside those buildings.
So instead of just one latent space representing catness, we could have a top-level layer for animal type, a middle layer for breed, and a lower layer for things like fur pattern and eye color.
That's a great way to visualize it. And this hierarchical structure can be really powerful for learning what we call disentangled representations.
Disentangled representations. That sounds intriguing, but also a bit like untangling a giant ball of yarn.
Think of it this way. Instead of having all the features of a cat jumbled together, we can separate them out neatly into different drawers. One drawer for fur pattern, one drawer for eye color, one drawer for tail length, and so on.
So each latent variable, each dimension in those latent spaces, is responsible for capturing a specific feature of the data, independent of all the other features.
Precisely. And this disentanglement can be incredibly valuable for applications like image manipulation. Imagine you want to create a picture of a cat with Siamese markings, but with the fluffy tail of a Persian. With disentangled representations, you could tweak the latent variables responsible for those specific features without affecting any of the other characteristics.
So I can mix and match different cat features to create my own custom breed. It's like playing with a digital genetics lab.
And it goes beyond just aesthetics. Disentanglement can also help us understand the causal factors that give rise to the data. By isolating specific features, we can start to see how they relate to each other and how they influence the overall outcome.
So we're not just creating cool cat pictures, we're actually gaining a deeper understanding of what makes a cat.
Exactly. And this kind of insight can be valuable in all sorts of fields, from biology to physics to economics.
Okay, so multi-layered latent spaces sound pretty amazing, but how do we actually train a VAE? With this kind of hierarchical structure, does it involve some crazy new math?
The good news is that the basic VAE framework we've been talking about still applies. We still have encoders and decoders, and we're still trying to optimize that ELBO objective, that balance between reconstruction and regularization.
But now we have multiple encoders and decoders, one for each layer of the hierarchy, right?
Exactly. Each encoder is responsible for mapping the data to its corresponding latent space, and each decoder reconstructs the data from that space. And the KL divergence terms in the ELBO now encourage each layer's latent space to stay close to its chosen prior distribution.
So it's like we're training multiple VAEs at once. But they're all connected in this hierarchical structure, passing information up and down the chain.
That's a great way to think about it. And this approach allows us to capture much richer and more complex relationships in the data than a single layer VAE ever could.
This is really opening up a whole new dimension to VAEs. I'm starting to see why they're such a hot area of research.
Absolutely. And the applications are truly vast. We've touched on image generation and manipulation. But VAEs are also making waves in fields like drug discovery, where they can help design new molecules with specific properties. And in anomaly detection, they can be used to spot those needle in a haystack events that don't fit the usual patterns.
And what about text and music? Can VAEs handle those kinds of data too?
Absolutely. They're being used to generate everything, from poems to code to entire musical compositions. It's really remarkable how versatile this framework is.
I have to admit, when we first started this deep dive, I thought VAEs were just about generating cool pictures. But now I'm seeing how they're really a powerful tool for understanding and manipulating complex data of all kinds. It's like having a Swiss Army knife for machine learning.
That's a great analogy. And the best part is that the field is constantly evolving. Researchers are developing new techniques and applications all the time. We haven't even talked about normalizing flows, which can make those latent spaces even more flexible, or hybrid models that combine VAEs with other machine learning techniques.
It sounds like we'll need to schedule another deep dive to cover all that. But for now, I think we've given our listeners a solid foundation in the world of VAEs. So before we sign off, let's recap the key takeaways. VAEs are a type of generative model that learns to represent data in a latent space. They use an encoder to compress the data and a decoder to reconstruct it. And by adding that special regularization term, they ensure that the latent space is organized in a way that's useful for both reconstruction and generation.
And by exploring more advanced techniques, like hierarchical VAEs and normalizing flows, we can create even more powerful models, capable of capturing the incredible complexity of the world around us.
It's been an incredible journey exploring the VAE landscape with you. I feel like I've gained a whole new appreciation for the power and potential of these models.
It's been a pleasure sharing this deep dive with you and our listeners. And remember, the world of VAEs is vast and constantly evolving, so keep exploring, keep learning. And who knows what amazing discoveries you might make.
And to our listeners, if this deep dive has sparked your curiosity, be sure to check out the show notes for links to the sources we discussed today, as well as some additional resources to help you continue your exploration of the fascinating world of VAEs. Until next time, happy deep diving.